Welcome to Sensors and Signal Conditioning. In this first lecture, we'll be talking about sensor characteristics. But before we begin, I want to clarify a few terms that we will be using. So first of all, what is a transducer? A transducer is a device that converts one form of energy into another form of energy. Okay, so in real life, you can think of many transducers. So for example, a fan converts electrical energy into mechanical energy. You could think of a light bulb, which converts electrical energy into light energy. You could think of solar cells, which convert the radiation of the sun into electrical energy, so on and so forth. Now, sensor is a subset of transducers. Now, a sensor is a transducer which converts any physical energy into electrical energy. So the output of a sensor is always electrical energy. Can you think of a few examples of sensors? Another term that is frequently used is actuator. Now, actuator is kind of the vice versa of sensor. It is also a subset of transducers, but it is a transducer whose input is electrical energy and the output is any other physical form. So for example, a light bulb would be an actuator because it takes electrical energy and converts it into light. Similarly, a motor would be an actuator because it takes electrical energy and converts it into motion. So let's say we have sensors. How do we evaluate whether a sensor is good or not? Can we think of some characteristics that we want in the sensors that we use and some characteristics that we do not want in the sensors that we use? So the first thing that we would want in a good sensor is that the sensor should be sensitive to only the measured property. I think it would be easy to think of this if I take an example. So imagine trying to measure the weight of a person. Let's say we use a force sensor to do this. This sensor measures the force that the person exerts on the device as he or she stands on it. But the catch is that the sensor is also dependent on temperature. The larger the temperature, the larger the output of the sensor. So on a hot day, you measure your weight and you think you're overweight. It rains in the night and the temperature drops by around 5 degrees Celsius and your weight reduces by 1 kilogram. Now, that's not desirable, right? So we want our sensor to be sensitive only to force and not to temperature. Okay. Another property that you would want to have in your sensor is that it should have a sensitivity that is adequate for measuring what you want to measure. So the instrument or the sensor that you're using should be able to measure the smallest change in the quantity that you want. Suppose, let's think about designing a thermometer that is used to control a furnace. The thermometer can measure temperatures up to, let's say, 3000 degrees Celsius. And it does that by measuring in around 10 degrees Celsius increments. Now, would this kind of a thermometer be useful to measure body temperature? Now, the thermometer is very good to use in a furnace, but I don't think it's very useful to measure the body temperature. Why? Because the body temperature in general varies between 32 to 42 degrees Celsius. And there is a world of a difference between a severely hypothermic person whose body temperature is 32 degrees Celsius and a severely hyperthermic person whose body temperature is 42 degrees Celsius. Our instrument does not have the sensitivity to measure the changes that we need to. So depending on the application, our sensor should have an adequate sensitivity. Ideally, we would also like a sensor to be linear. This means that our output should be a linear function of the input. So if we are plotting output and input, so if this is input and this is output, we would want the relationship to be something like this. And the reason why we want that is because it makes us easier to measure the output of the sensor. So you measure the output and then get the input easily by just a simple equation. You can relate the output and the input easily. There are some properties we do not want a good sensor to have. For example, we do not want the sensor itself to influence. Let's go back to the thermometer example and just think about a thermometer. Okay, so let's say we are using a mercury thermometer. So that's the mercury column and this is the bulb of mercury. And we want to measure the temperature of a ball, which is approximately this volume. Now, would that be a good idea? No, it won't be. Why not? Because to measure the temperature of this ball, the bulb of the thermometer has to get heated to the temperature of the ball, right? And when doing so, this is going to take away heat from the ball and reduce the temperature. So what have we done? We have influenced the temperature of the ball. And so our sensor, which is the thermometer, is influencing the measurement that we are making. And that's not a good idea. We do not want this. We also do not want a sensor to have an output that deviates randomly over time. I think we also do not want our sensor to consume a lot of power. Imagine the amount of batteries and the cost of running if sensors consume a lot of power. Imagine our mobile phone batteries draining out at 10 minutes if we make a call because the microphone is taking huge amounts of power from the battery. And there are other few things. For example, a sensor should not cost a lot, it should not be huge, it should not be toxic, but these are fairly straightforward and self-evident. In this next section, we want to look at sensor characteristics. Now, what do I mean by sensor characteristics? Sensor characteristics is basically knowing how a sensor behaves. There are two kinds of characteristics that we can talk about. One is static and another is dynamic. Okay? The static characteristic of a sensor is the behavior of a sensor when the input to the sensor is not changing. So imagine a sensor here. Okay, so this is a sensor and we are giving it an input and the sensor gives us some kind of an output, which of course is going to be an electrical output. So what we want to do is we want to keep this input a constant. And if we give a constant input, our sensor should give us a constant output, and measuring in this kind of static environment where the input and outputs are not changing gives you the static characteristics. Okay. Now, dynamic characteristics refers to the dynamic behavior of the sensor, or what I mean is how fast the sensor responds to a change in input. Now, again, take the same example. Let's say we make the input change suddenly and we look at the output and maybe the output slowly changes. And that gives you some idea of how the sensor behaves dynamically. Now, there are many ways of measuring dynamic response. Some of them involve suddenly changing the input from one value to another. Say, for example, keeping a thermometer in ice and suddenly taking it out and putting it in boiling water. Then we measure how long the sensor takes to give an output corresponding to the new input, which is the boiling water. So what we'll do in this lecture is look at static characteristics first, and then we'll look at dynamic characteristics. In this section, I want to talk about two kinds of static characteristics or ideas which are associated with static characteristics. One is calibration and another is linear. So let's imagine we have a sensor which of course gives an electrical output, and let's say in this case it's a voltage, and it gives the voltage in response to a physical quantity. To take a more concrete example, let's use a temperature sensor. This temperature sensor is called TMP35, and we'll be looking at this sensor in more detail later. Okay, but for now, this sensor measures temperature and gives the output as a voltage. So let's ask ourselves, what do we want to measure? We want to measure temperature. And what are we actually measuring, or what are we getting as an output of the sensor? Voltage. Okay, so if we have voltage, which is the output of the sensor, how then do we know the temperature? So there needs to be some kind of relationship between the voltage that we are able to measure at the output of the sensor and the temperature that the sensor is actually measuring, right? Some sort of equation which gives us the temperature when we put in the value of the voltage that we are measuring. So to really use this sensor, this TMP35, we need to know this equation. Without knowing this equation, we'll be measuring a load of voltages, but we will not be able to tell what temperature the sensor is measuring. How do we get this equation? This equation, of course, is the relationship between the input and the output of the sensor. And this process is called, the process of getting this equation is called calibration. Okay. Okay, so how do I do the calibration of the TMP35? Okay, here's what I do. I take the temperature sensor, and what I want to do is I want to give as an input a known temperature. How do I do that? One way would be to take a water bath with a thermometer in it. Now we know this thermometer, and this has already been calibrated, so we can measure the temperature of the water inside this beaker using this thermometer. And we change the temperature of the water by, let's say, heating it, or let's say by adding ice or something. And then we put our sensor, our TMP35, into the water bath. Okay. And while we have different temperatures in the water bath, we record the voltage output. And as we do that, we can plot a graph like this. On the x-axis, we have the temperature of the water bath, and on the y-axis, we have the voltage output of TMP35 or TMP36. Okay. And then we plot a graph. And from this graph, in this case, we've got a straight line, so it becomes much more easier. We can get the relationship. And this process that we are doing to figure out the relationship between the output and the input is what we call calibration. Now, what we want to do through calibration is to get a relationship between the output voltage and the input temperature. We want that so that when we measure the voltage, we'll be able to get the temperature that the sensor is actually measuring. Linearity is defined as the property of this relationship being a straight line. So the relationship between the temperature and the voltage, if it's a straight line, the sensor is called linear. Now, you do not always need a linear sensor. For example, our sensor could have a relationship between the input and output that is given by this red curve here, right? And that's all right. This is not a linear sensor. It's a non-linear relationship, and we can use such sensors as well. But linearity makes the relationship simpler so that the sensor is easier to use. In addition, what linearity does is that it makes the sensitivity of the sensor constant throughout the range of the input of the sensor. We'll just define sensitivity in a few slides. Let's continue our discussion of sensor characteristics, and remember we are talking about static characteristics, and let's think about accuracy and precision. Now, these are very primary and one of the first static characteristics that we need to understand. Now, accuracy of a sensor tells us how close we are to the true value of the quantity that we are trying to measure. Precision, on the other hand, gives us a measure of how close the outputs of a sensor are when successive measurements of the same quantity are done. That is, it is the capability to give the same results when we do the measurements again and again. Okay, so to understand the meaning of accuracy and precision and their difference a little bit more, let's use the help of the most famous outlaw of all time, right? Robin Hood. If you don't know the story of Robin Hood, that you need to read it or watch movies about him. But for now, all you need to know is that Robin Hood was an excellent archer, a marksman par excellence, right? And so we asked Robin Hood to shoot arrows at a target. What do you think the result will be? He is, of course, a marksman par excellence, so he'll be right on target again and again, right? So what does that mean? It means that he is close to the center, which means that he's exactly where he needs to be, so he's accurate, and all his arrows are going to be close to each other, which is precision, which is he can repeat his shots again and again. Now let's apply this to a sensor. An accurate sensor measures the true value of the quantity that it is trying to measure. A precise sensor will give the same output how many ever times you measure this quantity. Now let's make this a little bit more interesting. Imagine Robin Hood is actually shooting in an archery competition in Nottingham. And he shoots perfectly as before, but he's duped. The target is not what he sees, but another behind it, which is offset a few inches. And of course, we all know who's behind it, the wicked Sheriff of Nottingham, right? Now, in this case, think about accuracy and precision. Now, the true target was this point here, right? But all of Robin Hood's arrows are hitting at approximately this point. So he's not really accurate. So he's not accurate. But are his arrows close to each other? Yes, they are, which means he's still got repeatable measurements or repeatable hits, which means that he is precise, but he's not accurate. Again, accuracy measures closeness to the center, and precision measures how repeatable the measurements are. We can have accuracy without precision, and we can have precision without accuracy. So what about this pattern? Let's say you have this. Is this accurate? Is it precise? It's definitely not precise because the measurements are all over the place instead of being in the center, right? Is it accurate? Well, probably it is accurate, even though it's not precise, because it seems as if all the hits are clustering around the center. So probably accurate, but not precise. Okay, let's take another example. Let's see, what about this case? Is it precise? Are the measurements close to what they should have been? Are the hits close to what they should have been? No. Is it accurate? Where do these yellow dots cluster around? Probably somewhere here, which is not the center. So this is not accurate and this is not precise. Right? Now, so let's think about this idea of accuracy and precision in terms of, let's say you're measuring force, okay? And the force that you want to measure is at this value. So this should be the output of the sensor if it was giving you the right values. Now, for an accurate sensor, the output of the sensor should be as close to this red line as possible. So for example, you will have outputs which are like this, very, very close to this line. Now this is an accurate sensor. The measure is how close it is to the true value, which is this red line. Okay. A sensor which is not accurate could have, so this is the true value, and it will have values, let's say, somewhere here. So even though the values are almost the same, these values are not close to the true value, and therefore this sensor is not accurate. However, this sensor is very precise because the measurements that you're getting, even though they are the wrong values, are exactly the same every time you're doing the measurement. So this is a sensor which is accurate, but which is not accurate, but which is precise. Let's think about how the characteristic would look for a sensor which is not precise. So here's the sensor characteristic. This is the true value that you want. And if you have values like this, right, all over the place, so this is not precise because the readings are not very close, very repeatable. They are not the same. There is a lot of error in the readings. However, this may be reasonably accurate because if you look at these, this probably is centered around the true value. Hope that helps you to understand what accuracy and precision mean. So one of the ways that I kind of confuse between accuracy and precision quite a lot. So I use this acronym PTAC. I don't know whether you know blue tack. Blue tack is a substance that you use to stick things on the wall. So PTAC, precision means together, accuracy means the center. Okay, precision means together, accuracy means the center. The next static characteristic that we are going to look at is called sensitivity. Now, sensitivity is the amount of change in output for a small change in input. So think about it this way. So let's say we have a sensor whose characteristic, whose relationship between input, this is the input, and the output is given by the curve on the graph. Say the input changes by a very small amount, delta x, and corresponding to this change in input, your output changes by delta y. So the sensitivity of this sensor is essentially given by dy over dx. And of course, it is at a point x equal to xa, which may be the point at which around which you're changing the input. Now, of course, from this you can see that sensitivity may not be the same for the entire range of the input, and especially in this curve. So the sensitivity is very low in this region, so very low. And in this region, the sensitivity is quite high, and it again reduces here, right? And that is the case for non-linear sensors. However, if you had a linear sensor, the sensitivity would have been a constant for the entire range of inputs. Like it is shown here. So here are two linear sensors. A sensor which has more higher sensitivity, so this sensor has a higher sensitivity, it has more change in output for the same input than the sensor with lower sensitivity. So let's say you want the same amount of change in output For a high sensitivity sensor, you will have to change the input a little bit, while for the low sensitivity sensor, you'll have to change the input quite a bit. So one of the advantages of high sensitivity sensors is that you can measure very small changes in the input, right? But are there some disadvantages of high sensitivity sensors? Yes, definitely. One of the problems with higher sensitivity is that it reduces the range of the sensor, which is to say that it limits the values of input that we can use the sensor for. If it's a low sensitivity sensor, we can use it for a large number of values, while if it's a high sensitivity sensor, you will only be able to use it for a small range of values or a small I'll leave you to think about why that is. I think the clue is you'll have to think about saturation. Let's talk about now resolution is the smallest change in input which would produce a detectable change in output. Notice what we're saying here. Let's say we have a way of detecting the change in the output of the sensor. So perhaps, take for example, that we are looking at the height of the mercury column in a mercury thermometer. What is the minimum detectable change in output? And the input that corresponds to this change is called the resolution. Okay? Let's take an example to think about this a little further. So if I'm measuring the position of a point inside a circle, let's say we are using these two grids, grid 1 and grid 2, to help us do that. We want to find out what is the distance of the point from the center and the angle from the positive axis. Which of the two grids has a higher resolution? Definitely grid 1. Why? Because in grid 2, I can only measure angles in increment of 1 degree Celsius, right? And we can measure the distance in radial increments of 0.5. But in grid 1, I can measure angles in increment of 1 degree and distance in increments of 0.1. So this has a much higher resolution than this. We are talking about sensor characteristics, and we are specifically looking at static characteristics. In this part, let's look at what we mean by sensor. Now, the idea of input impedance of sensors is an extension of the idea of input and output impedances from electronics. Input impedance relates to the idea of the sensor influencing the measurement that we are trying to make. We talked about this when we discussed the characteristics of a good sensor. So input impedance is the measure of the sensor's ability not to interfere with the signal that it is measuring. So let's think about measuring the temperature of the body. And let's say the temperature of the body is T1. Let's say we want to measure the temperature of the body. The sensors that we use are at a different temperature to start off with, called T2. And we are trying to use sensor 1 or sensor 2. Which of these sensors would you prefer? Why? Now, we would definitely, if you think about it, you want to use sensor 2. Why is that? Because if we use sensor 1, the sensor 1 has the same, let's say, mass as that of this object. And when you bring this close together, what is the joint temperature of the body and the thermometer going to be? It is going to become T1 plus T2 over 2, which means that my sensor 1 has actually influenced the temperature of this object. And therefore, the input impedance, therefore we say that the input impedance of sensor 1 is so small that it is actually loading or interfering with my object that I want to measure. On the other hand, sensor 2 will be very good because sensor 2 is so small, it will hardly take any heat from from T1, and therefore the temperature of T1 is not going to change. In other words, we would say that the input impedance of sensor 2 is high, and it is high enough to not allow any loading of the input. So the input impedance of sensor 1 is low, and the input impedance of sensor 2 is high. So we've been looking at sensor characteristics, and the last static characteristic that we will look at is errors. There are two kinds of errors that we can talk about. We can talk about systematic errors, and we can talk about random errors. What are systematic errors? Systematic errors are errors that do not change when the measurement conditions do not change, or they change predictably when the conditions change. What causes these errors? It could be the instrument, or it could be that something is faulty in the way the measurement is being done. That is, there is something wrong with the method. So the example of Robin Hood missing the mark because of the evil sheriff's plan was a systematic error. It was not random. The error was predictable if you knew what was happening. The interesting thing about systematic errors is that they are very difficult to detect. The only way to find out if there is a systematic error in the measurement is to use different instruments or different methods, or to get different people to do the measurements. We do not know the errors until we compare it with the measurements made by another instrument or method or person. On the other hand, random errors are random. These are errors that remain after eliminating systematic errors from a system. They could be caused by factors that are not under our control. And because they are random, we expect that positive and negative errors are equally likely to occur. The larger errors are usually more unlikely, because small unknown phenomena usually causes small fluctuations in the measurement and not large ones. And if we look at errors in a large number of measurements, we will see that the mean of these errors approaches zero. This is because there is no pattern to the error. It's just random, and you expect that the positive errors would cancel out the negative errors. So in this lecture, we are looking at sensor characteristics. We have already looked at static characteristics. Now we are looking at dynamic characteristics. Dynamic characteristics describes the behavior of a sensor when the input changes. So we are interested in how the output changes over time in response to a change in input. Why do we need to study dynamic characteristics? So take, for example, a vehicle suspension. So while driving on the road, there's a sudden change in the road profile. Okay, because of some road construction work, there is a change in height of the road by 1 centimeter very suddenly. If you're traveling on the road, you're going to feel a jerk, right? The type of jerk that you feel depends on the dynamic characteristic of your suspension. You may feel a gradual change in the height of the body of the car, very smooth, which means that your suspension is working very well. Or you may feel a sudden jerk and the body of the car bounces and slowly goes back to the normal position, and so on. So essentially, the output of a sensor to a sudden change in input could change very slowly, or it could change very quickly before settling down. And we want to know how the sensor behaves. describe the change in output with respect to time as a function of the change in input by using a differential equation, okay, which is shown here. You could also do kind of a frequency domain representation of the differential equation, which is shown here. And as you can see, that describing the dynamic characteristics can actually be very complicated mathematically. However, what we do is we approximate the dynamic characteristics of our sensors. And most sensors can be approximated to zero order, first order, or second order responses. And we'll see what that means. Let's look at a zero order response. A zero order system is a system whose output is proportional to the input. Okay? So the time profile of the output is exactly the same as the input. So if the input changes like this, the output also changes like this. If the output changes like this, input changes like this, the output also changes in the same manner. So you can describe this system with only one parameter, and that is called the static sensitivity. Or you could call it the gain of the system, the gain of the system. So an example of a zero order system would be a potentiometer. So if we are trying to measure a displacement, and here's a resistor, and as this wiper moves, the resistance here, the output resistance that we're taking is measuring, or you could convert the output resistance into a voltage as well. Okay. Now, so if we have a step input is a sudden change in the input as shown here. Step input, the output is also going to change by a step. Of course, there's going to be a gain, but the time profile is exactly going to be the same. In the frequency domain, the transfer function, that is the ratio of the output to the input, is going to be a constant. But that's not the way a thermometer works, right? A thermometer doesn't work like a zero order system. So let's think of a thermometer. And here's the bulb of mercury. It looks like a very big bulb, but I think it's all right. Now, if you put it at a new temperature, the column of mercury rises up slowly. It doesn't go at the same speed at which the temperature actually changes. This is because the thermometer can be approximated as a first order system. The mathematical relationship of the first order system, since a first derivative appears in the differential equation, this is called a first order system. So in addition to the static sensitivity, which we had in the zero order system, we have another term called the time constant, which kind of defines the behavior of this system. So the behavior of the first order system is shown here. So if we have a step input, step change in the input, the output would change slowly. It would take some time for the output to reach its final steady state value. And depending on the time constant of the signal, the speed of responses may be different. So here's a faster system, and this one is a slower system. On the frequency domain, you can see that for small frequencies, the gain is a constant, and then as you go to higher and higher changes, the gain becomes lower and lower, as you would expect, because the system is not able to respond as fast as the input is changing. Let's look at the second order system. The largest differential in a second order system is the second differential. Um, and the parameters that define a second order system are static sensitivity, undamped frequency, and the damping ratio. An example of a second order system is a spring loaded weighing machine. What happens when a weight is suddenly placed on it? It starts to oscillate, right? And the oscillations will slowly die down with time. So in response to a step input like this, the second order system can respond in three ways, depending on what the damping coefficient is. If the damping coefficient is less than 1, then you have oscillations like I'm showing here. If the damping ratio is greater than 1, you have a response which is very similar to the first order response. And for a damping ratio which is exactly equal to 1, you have what is called the critically damped system. Okay? So this system, which is oscillating, is called underdamped. This system, where the damping ratio is greater than 1, is called overdamped. And the one which is on the border with damping ratio equal to 1 is called critically damped. Knowing the kind of response that a sensor has, either a zero order or first order or second order, it helps us to know how the sensor is going to behave when the input is changing. And that helps us to know whether we can use that sensor for measuring a particular kind of an input. Whether we can capture the changes in the input that we want to